We often wonder where all the vast and ancient alien civilizations are, but could it be that they've migrated far away in space or time, or even journeyed beyond our cosmos? The Fermi paradox is all about asking where all the aliens are, and one option is they may originate all over the place, but tend to migrate to places more favorable for their civilizations. This might be densely packed star clusters, or even migration to the vastly larger and denser galactic core, or it might go the other way, out to the galactic rim, home of scattered stars or ancient globular clusters, and home to civilizations wishing to utilize the coldness of empty space far from stars or hiding to the end of time. Perhaps they flee in time too, to earlier times in our universe, or to that cold time at the end. Or they may migrate to other universes, or even more fertile dimensions or layers of reality. And far from us, they may not be easy for us to see, or have any desire to reach out to us, figuring we'll eventually migrate their way one day too, if we overcome the challenges needed to become an interstellar species. We'll be exploring all those options today as we contemplate the effects migration might have on the Fermi paradox, and the broader effects it might have on civilizations doing the migrating, and why they might have. The Fermi paradox is the big question of where all the ancient and immense alien civilizations are in a universe that seems devoid of them, and yet is far older and unbelievably larger than our small, pale blue dot of a planet. Many answers have been discussed, including that we might simply be unwilling to admit they exist and visit us regularly, and most focus on either why advanced technological civilizations would be much less common than we might expect, or prone to blowing themselves up, or simply unable to colonize space beyond their native star system, leaving our galaxy full of perhaps hundreds of isolated alien planets scattered around unable to hear each other. At such a density, aliens would generally each have around 1 billion empty star systems surrounding them and out to a few thousand light years. Any signal would take as long to reach another civilization as our civilization has recorded history, and as long to travel back, and we can imagine they might not bother transmitting, especially as they would need to be a strong signal and they may tend to have a half-life on their civilization, at least for continuing transmission. How many centuries of transmitting the high gigawatt range of power consumption is your local planetary government going to continually fund, even as it goes through untold numbers of changes in leadership, peaceful or violent? This is a fairly common viewpoint on the Fermi paradox, and more or less the original viewpoint of Enrico Fermi and many others who lived during the arms race and space race of the Cold War. We had hydrogen bombs, he helped design them, and we had no moon landing yet. So imagining reaching other star systems was mostly a thing of science fiction, not science. After the moon landings, we began wondering if getting to other star systems and colonizing them at slower than light speed, journeys of many decades if not millennia, might indeed be possible, and of course a lot of the episodes on this show focus on the idea that these migrations are possible. But this assumes a migration from the homeworld out, and that we are listening for life nearby us, or that would be trying to reach out to our area of the galaxy. Today we'll be considering that these migrations might not be omnidirectional out from their homeworld, but focused on more fertile territories. And while I think the evidence favors colonizing everything eventually, it is worth noting that many of our civilizations have dwelt next to more barren and less fertile prospects for millennia, and made few inroads into settling mountains. Many folks live in the shadow of a mountain, but most folks who live on one went there for the isolation, and thus might not be prone to sending out messages, building up huge civilizations, and leaving obvious signs of their presence. Migrating to star clusters might be a preferred strategy, for instance. Rather than trying to send expensive and immense arc ships out to every star inside a region where they are each several light years apart, you might send one very large mission to the nearest star cluster, or a handful to the nearest ones. There's around a dozen open clusters within 1,000 light years of us, and none will have any life in them, since they are full of young stars that will be just done having the bigger ones go supernova, and planets will just be cool enough to permit habitation. Here you would have hundreds of systems within perhaps a dozen light years of each other, and many separated by less than a light year, often just light weeks, even when discounting binary and trinary systems. This reasonably permits an interstellar civilization to exist in that cluster. As to why you might be doing this, that is a bit trickier. If you are skipping on colonizing neighboring star systems because they are too far apart, then migrating all the way to a cluster of hundreds or thousands of stars because they are packed closer, while skipping hundreds or thousands of stars closer to your homeworld, that does seem a bit dubious. It is easy enough to imagine folks making a big effort to get to one of those clusters as the galactic equivalent of a fertile river valley, but you're passing up on a lot of real estate that should be as good as your home system in the process. One scenario might be that you do indeed colonize those stars near your homeworld, but in keeping with Pancosmorio theory. See our episode on it from earlier this year for details, but the theory tends to assume it is harder to successfully colonize the further you get from your homeworld, in terms of not just getting there but making the colony work and pulling off terraforming a new world. That Earth really is the only terrestrial biosphere, and anything we make is going to need a lot of help and take very, very long times to become truly stable on its own, and be fairly alien to Earth at that point too. You might get your outward expansion petering off after a few dozen light years, and only really taking off when it envelops a star cluster, and nobody bothers trying to colonize anything but those going forward, and even that might stop as your next neighboring wave of clusters might be too far away to bother, and more so in the eyes of a cluster civilization which is used to stars being closer together. In keeping with our discussions this year of the Chronos scenarios and interdiction hypothesis, where a civilization tends to view its outer colonies as a threat or danger, and the more so the further out they are from where they can exert some control and influence, and thus stop making efforts to create them or help them, potentially even banning them. Indeed, under our modified perspective of interdiction, they might even aggressively mine out a larger radius around their core systems to enrich the core and make that area around them into a buffer that cannot support any serious rivals or empires or invasions. Star clusters are already set up like that, so if this is the way colonization works out, we might see only this interdicted desert oases around homeworlds, and those nearby clusters colonized by folks who in turn have no reason to fund any efforts to colonize more distant clusters. You don't really care if someone does, because a rival cluster that far away has little reason to invade down the road, and little real ability to do so, given this scenario only really works if space colonization and travel is quite hard. You can send a small fleet of Ark ships to tap an unclaimed treasure, but you can't send a giant armada big enough to seize that treasure from an existing empire already hoarding it. If that was practical, colonizing every star would be too. Speaking of battle fleets and armadas, you might be fleeing something as well, in which case running a long way makes sense and you might as well aim for something nice on the end of that exodus. But that something is presumably in control of your homeworld and space capable, or you probably would have just fled to the nearest decent star. You're assuming they'll be claiming that system themselves, or will remain militant towards you if you're that close, and that is reasonable and justifies the migration, but not the lack of migration to other nearby star systems. From a Fermi paradox position, our reasoning for not seeing these civilizations is they bypass most stars and the galaxy is fairly empty of them as a result, so we have to establish a motivation why that would occur rather than colonizing everything. They may have opted to move their whole home system to a more fertile place though, and may have picked the arguably most fertile spot in the galaxy, its center. Core migration makes a lot of sense. Things are packed in as tight as any cluster down there in the core, and it's vastly larger. Indeed, deep in the core region of the central bulge, star packing is not only more than 1 per light year, but more like 1,000, making interstellar civilizations very easy. This is where we are going to suggest moving our whole star system, because while you might go migrate to the core 27,000 light years away, it would seem like that's something you would do while colonizing normally or jumping star clusters. Even if one element of your civilization set off for the core on their own from the outset, everybody else might proceed to colonize normally, and that rather negates the Fermi paradox considerations. If you do colonize normally, that doesn't mean you don't go for the core. It is insanely valuable, so much so that if you could jump there, you might not ever bother with the rest of the galaxy because it would just be a scattered hinterland in comparison, while admittedly a hinterland still containing considerably more resources than the galactic bulge and core region. Now, I think most folks would assume interstellar colonization with spaceships was easier than moving your entire solar system, and the answer is actually no, not necessarily. If you're new here, welcome to SFIA, where moving stars or entire galaxies gets shrugged off as doable, but faster-than-light travel is frowned upon. I'll explain why moving stars isn't too hard in a moment, but now is a great time to hit those like and subscribe buttons and to grab a drink and snack, because we're going to be here for a while. If tomorrow I invented a machine able to land on a rock and mine and process it into tin foil, or aluminum foil, or some other metal foil or mirror, I have everything I need to move an entire star. I don't need to invent artificial fusion or complex beaming arrays, or try to move a ship on a wave of nuclear detonations, then let it drift through the void without resupply for a century before nuking it some more to stop, and then hope whatever is left in terms of people and resources can carry on a space program more elaborate than our modern one to get landed on a planet which then needs terraforming efforts that would make any environmental or eco-engineering project we've ever attempted look like a kid's jigsaw puzzle in terms of relative effort and complexity. Instead, I just need a machine that can mass-produce metal foil from asteroids. The simplest approach, though the slowest, is the Shikata thruster. It takes the light coming off a star and bounces it off of mirrors all in one direction to create a net thrust. This is a net thrust on the whole system, as the mirrors stay gravitationally tied to the star. They get shoved on by its light, but the star pulls them back gravitationally, while they pull that star their way too, moving the combined system so long as they are heavy enough not to blow away. It is a very small thrust, and would take you on an order of 1 billion years to move our star system this way to the galactic core, but that would be acceptable if nothing else was available. It's great for intergalactic colonization too, because it takes half of forever to speed up and slow down, but can get to fusion drive speeds, and means you're migrating your whole solar system so its arrival in the core, or an open cluster, or globular cluster, or different galaxy means you now have your entire star system effectively teleported into this dense area of stars, along with all your infrastructure. There are other faster options too, even without assuming some convenient portal or teleporter. We have a lot of options like the Kaplan thruster or Helios drive. See the Advanced Spaceship Drive Compendium for details. Those obtain lower final speeds but accelerate much quicker by using superheated stellar matter as your propellant. You engage in something like starlifting, which is a great way to get access to many planets with resources, and generally lets you move around a galaxy on a timeline of several million years instead. You convert something like 99% of the sun's energy to propulsion. Don't worry, we use less than 1/1000th of it, so there's plenty to spare. And you take matter off the surface magnetically using the sun's own power, remove the heavy elements you want, and use that remaining energy to blast that propellant out of very large and high-powered ion drives or linear accelerators. This is more high-tech, but uses the same technologies we would use for normal interstellar spaceships beyond the post-nuclear level like the Orion drive. So if you can do the one, you can do the other. It's just scale. And it gets around all the other issues trying to colonize other systems has, like supporting a civilization all the way there through the endless night of deep space, and trying to create a world with whatever you've got left when you arrive. For timelines, the sun gives off 4 times 10 to the 26 watts of power, and mass is 2 times 10 to the 30 kilograms, so its power to weight ratio, or power to mass, is actually very low. It's worse for smaller stars, and easier for bigger ones, as brightness and power of a star rises very sharply with mass. I don't think you'd have a problem getting an exhaust velocity of 1,000 kilometers per second. That's only about double the normal speed of solar wind, which is fast enough, but means you probably need to eject at least a few percent of your sun's mass to achieve that, and it only produces so much energy at a time to fuel that expulsion. So even if you're doing this very well, you probably need around 1 million years to get to the core, but that's nothing in galactic timelines. And if you are using this approach, it's because other methods of star travel have proved unviable, or you've decided that you want to put your home system in a cluster or core to make it the center of a tight packing of stars, rather than migrating to them with ships and abandoning your homeworld, or letting some splinter of your civilization claim the prize. This is an approach we would also expect something like a hive mind or single massive computer mind to use too. since it could migrate itself there and potentially have a single vast mind that's sprawled over hundreds of thousands of stars, even if signals might take a few years to move from one side to another. It just means it has a lot of the equivalent of reflexes and subminds handling minor stuff under its grander, insanely huge, and yet also slow megamind. We discussed this more recently in Jupiter Brains and Megaminds, this month's Nebula exclusive, but the key is that if you sprawl over large distances, ones that would take a signal longer to travel than your needed reaction time to a given event, you simply have lower semi-autonomous levels of your mind that act as your reflexes or even regional coordinators. In national terms, you don't have a vote by Congress to decide if one pencil should be bought in Arizona or one passport approved, and it may be years before any report or audit reaches them related to that event, even if it did elevate to their layer. They are still you, but you, as an entirety, might be some million star system supermind several light years across, so you have a lot of local defense systems that can act on their own. Same, your conscious mind does not individually authorize each new hair to grow or blood cell to be produced. Your immune system's equivalent to foot soldiers do not radio up to high command before engaging every virus or microbe. But these don't have to all be sub-intelligent. You have an hierarchy, basically your automated defenses, under the equivalent of a squad sergeant that's smarter and covers a wider area of several of those automated ones, but is a bit slower to react, who in turn is grouped with many more squads until you have a slower but smarter lieutenant over a platoon of them, and these in a wider company under a yet slower but smarter captain, and so on until you have your regional generals who might oversee everything in that star system and need days to react. You may have such hierarchies for not just defense but other areas of interest, like logistics, or working on smaller chunks of big problems, either under that same hierarchy or a completely different one, like a different department in the cabinet of your mind, complete with liaison minds between those departments and even rivalries about suggested advice or priorities. So this lets you have a bigger mind but retains many disadvantages, and you are, for lack of a better phrasing, vulnerable to your subminds getting treacherous or crazy. So the decision to further widen your mind, especially in ways that sizably increase time lags, requiring more layers of subminds, may be one where you find yourself saying no. So both huge megaminds and mega civilizations, while having lots of apparent reasons to grow, do have at least some motivations not to grow as well. Time will tell how the practical math of that works out. A lot of Fermi paradox solutions assume they is some civilization reasonably like our own. We fully acknowledge that they might be incredibly alien, but there are limits to our intuitive grasp. It is entirely possible the norm for civilizations that avoid nuking themselves is to create an AI that eventually gets out of hand and takes over. It may wipe us out or keep us as slaves or pets, or it might just be very devoted to us but is so good at its job and smart that we always take its advice on big things, and it tells us expansion out beyond where we are is dangerous and a waste of time, and sincerely means it, but mostly because it doesn't think it can safely expand its own mind out beyond that distance and doesn't trust any rival minds it might make not to become a problem. They say children are your path to immortality, but when you're already immortal, your children just grow up to be rivals, and that's something that might weigh heavily on the minds of both AI and civilizations with life extension technology, which I suspect every civilization would achieve before or roughly around the same time they got interstellar travel technology. Having offspring is a vital thing to nature, but generally very dangerous to the individual doing it. Indeed, for a lot of species, it's universally lethal. We are wired to do it anyway, and also wired to be very interdependent on each other socially. A singular megamind is not by default going to feel this way, and any given problem that it feels it cannot solve in spite of its immensity has to be weighed against asking if it really benefits enough by potentially solving that problem to destabilize its current mind by further expansion or introducing rival cousins. And this is going to apply to any such mind, as whatever its purpose, whether it's purely selfish or making paperclips, or even if it's a caretaker AI tending a Dyson swarm of human space habitats, it has to have the goal of self-preservation, because "don't die during the mission" is the unspoken command of any assigned mission and the first rule of warfare, as even a kamikaze run requires you stay alive until that last step. Something of a tangent, again see that episode for details, and our upcoming one on Caretaker AI, but we need to be mindful that a lot of our Fermi Paradox solutions revolve around potential solutions not explaining why nobody has colonized the big chunk of space around us, or including us for that matter, and these solutions always boil down to three options. Space is empty around because nobody exists close enough in time and space to have colonized it yet, or because they exist there but it's impossible or impractical to expand, or because they just don't want to expand. These give us a reason why further expansion beyond a certain specific physical size was impractical or even dangerous, and also a few places far from us where you might decide to do that expanding, and hence we don't see you and you don't really care if we do anyway. In all probability, the only value other civilizations offer is interesting stories in biology or culture, and an outside hope they might figure out some awesome new science that you did not and be willing to share it if they did. Keeping in mind that if you ask about a tech, their reply might take tens of thousands of years, much less than would presumably take you to research it yourself. And if they can hear your radio waves that you send them, the odds are good they are already in an era where they can record their history in detail and will advance to digital storage pretty quickly, so you're not so worried they're going to lose interesting bits going forward, and before that you had no practical way to reach them anyway. So if you want their art and history, by the time they could provide it to you, the rush is gone since they have so many recordings and backups of them. And again, this option encompasses the idea that space travel is very hard, and maybe even so hard that you have to turn your solar system into a spaceship to make it work practically. Our next topic, rim migration, openly contemplated that idea from the outset. Way back in 1950, when we knew much less about galactic mechanics, Arthur Hogue discovered the first ring galaxy, which we call Hogue's object, and looks less like a spiral galaxy than a big thick ring around an empty space with a big galactic bulge in the middle. This was strange, so as we often do, we asked if this might be a sign of artificiality, and the reasoning goes that people might not just migrate to a galactic core, but to the rim of a galaxy. They might turn their star into a big spaceship and move it, and since you probably can more easily colonize neighboring stars than move an entire star, people colonize these and they eventually move them coreward or out to the rim. Indeed, even a star cluster might be moved as a big chunk. It's not too hard to do, and those younger, shorter-lived stars in most clusters make for better engines anyway, so you burn them out in the travel. Indeed, taking some giant star 10 times more massive than our own and converting it into an engine that's going to blow 90% of its matter away as propellant might be a great way to get a nice normal yellow sun like ours out of it, while moving it quickly across the galaxy or out of the galaxy, and also removing potentially hundreds of thousands of planetary masses worth of metals from it for you to use in the process. Moving your solar system out to the galactic rim has a lot going for it. There's some ancient clusters out there that are ripe for colonization. Omega Centauri, a globular cluster fully 17,000 light-years away, is visible to the naked eye and contains an estimated 10 million stars packed into a glob about 150 light-years across. It is the largest one in our galaxy, or on our galaxy's edge, and quite probably was a failed proto-galaxy of the many of those in other dwarf galaxies slowly absorbed to form our own. But there are a couple hundred of them and they'd be very valuable turf, especially if you need a place to flee to, which is one reason for rim migration. Indeed, it was the penultimate bastion of the losing side of a galactic war in our episode Extragalactic Sanctuaries. For a lot of civilizations, one star, or one cluster maybe, is enough, and if you're moving many of them out to the galactic rim, you can artificially stick them into tighter, stabler, and safer clusters out here too if you want. You might even move them as a pack where the bigger ones were doing most of the pushing and drain them all down to your ideal star size. Now we know more about galactic mechanics and ring galaxies aren't so mysterious anymore. Those galaxies are not empty in the middle. We're seeing a big wave of star formation moving out from the center, and big bright blue stars can often be a million times brighter than our own sun. And very short-lived, so it's just drowning the normal regions of that galaxy out visually. Frequently it's a byproduct of some galactic collision event too, which can make the ring less central. Hoag's object is an almost perfect circle out from its center, making it seem likely something in the center set off the star formation wave, but others can appear to emerge mid-galaxy, so the ring looks more like the bulge is a gemstone on it than its center, and that's easy to go, aha! They're spreading out from some homeworld that, like ours, is in the middle of their galactic disk. Which is also a possibility, but we have decent natural explanations now, and the expanded data doesn't look like a migration, just a star formation wave. And those big bright giants are usually viewed as non-ideal for civilizations or machine minds. We could debate that. We examine that more in our episodes on colonizing giant stars and killing stars. But the usual notion is that if you make stars, it's not the big and short-lived kind. Now, the real key of rim migration as a Fermi paradox solution is that it tends to assume the ultimate goal, or unintentional convergence, of intelligent life is to larger and more powerful minds. Essentially the omega point concept, which usually implies purpose-built computers that probably run on atomic scale switches rather than our meat brains. Tiny switches and devices hold up better in cold environments because heat is literally random motion of particles slamming into each other, and that tends to make things wear down faster. More importantly, we have Landauer's limit on computation, which we've deep dived in other episodes like black hole farming, and more in that Jupiter Brain and Megaminds episode from last week. But comes down to saying that a computer that's running at half the temperature can produce twice as much calculation as before with the same energy, a tenth the temperature, 10 times the computing, and so on. All things being equal, if I have a finite fuel tank, I want to get the most calculation, or thought, or experience and living that I can get out of it. So going to some place colder where I get better efficiency makes sense. You can only get so cold. The cosmic microwave background radiation, for instance, is at 2.7 Kelvin, so you can't go below that without active cooling, which takes energy. Your air conditioner uses a lot of energy to remove heat energy from your house and dump it outside, and that defeats the advantage of going colder than 2.7 Kelvin. And in practice, you can't quite get there either, because if you're doing any power generation and local usage, you've got that plus the CMB to get rid of. As you are absorbing that CMB radiation everywhere, it's basically your lower limit. Clever folks are probably thinking, well, we can do better in a lab. Can't we stick our processors in an ultra-core unit made by active cooling, and all the other support materials can be at higher temperatures? And the answer is yes, and that can raise the bar a bit, but only by some amount, much like one step better on a transistor size would. Those processors in your core tank are still producing heat every time they work, and still need time to cool back down to flip again, and cooling off takes longer the colder you are too. So you benefit by going someplace where space is quite cold, where you can build your planet brain or J brain or M brain or S brain, and the galactic rim is a lot colder than the center or mid regions. I should note that cold is a bit of a misnomer here, as we tend to think temperature, but we actually mean total heat per volume. Space is not cold, in terms of thermometer temperature. It's constantly flooded by noontime sunlight near us, for instance. It's just so low density that the hot particles bouncing around this volume are so few in number that they just don't represent much transfer of heat. You could be in a nebula that's 1,000,000 degrees, indeed the ones on the edge of the galaxy are generally that hot, and still freeze to death because they are so few in number that they strike your spacesuit or habitat and transfer heat far less often than you radiate your infrared waste heat of photons. Any object has surface temperature that controls its heat radiation, one of 3 ways to get rid of or gain heat. The other 2 are convection and conduction, and what we mostly use for cooling and heating on Earth. But that third, radiation, is the only one that still operates in a vacuum. Conduction requires you to be touching something, and convection is those tons of bouncing gas or fluid particles hitting the object, like air or water, and transferring heat around. Heat, in nebula terms, means how fast particles are traveling on average and random compared to each other, and out in the deep void at galaxy's edge, that's all the random particles moving fast enough not to be pulled down into the galaxy, and yet not quite fast enough to escape into extragalactic space. They thus have a very high temperature, but that area they are in has virtually no heat, just a handful of super hot particles that virtually never hit anything. Alternatively, deeper inside the galaxy, there's a lot more background radiation, more ambient starlight, denser gases, and so on. It's just hotter, in terms of heat energy present in a volume. Out at the rim, there's virtually nothing, but it's all super hot in terms of small particles moving randomly and quickly. So the notion here is that you pack up and go to the galactic rim, and once there you can maintain corridor calculating temperatures more easily and get more bang for your computational buck. You have brought everything you need with you, as a ring galaxy might indicate if artificial, or only use what's out there, which is hardly devoid of resources, but nowhere near what the core or even galactic disk have. So the usual objection is that whatever your savings are there, it's better to run this process in the main galaxy, and just cope with the higher heat and loss of efficiency, which also circumvents some of the slowness issue, since heat radiation goes with the fourth power of temperature, so a switch operating at 10 Kelvin that went up to 11 Kelvin takes 10,000 times as long to drop from 11 back to 10 as one that was at 100 Kelvin and went to 101 Kelvin when it flipped. And there's a lot to be said about operating faster and hotter. Of course, time has no real end, and many might opt to migrate to the end of time to run their civilization. After all, in the starless universe, where all the matter left is either in black holes or stockpiles, and everyone's mind runs on machines, time passes for them at the rate those switches flip, so it hardly matters if that takes a nanosecond each or a year each, and their true effective lifespan of time they will experience is based on how long their stored fuel and supplies last. So if you can exist for 1,000,000 years at normal speed, great, you live 1,000,000 years. If you exist at 1,000,000th of that speed, but get 1,000 times the efficiency out of your fuel, you experience a lifetime of 1,000,000,000 subjective years, and in the outside universe, it lasts 1,000,000,000,000 years. So a civilization, or individual megamind, or individual regular but uploaded mind, might flee to the depths of space and time with all the treasure they can carry, like fuel, and eventually be safe from thieves from Hubble expansion and travel time, and just run on minimum as the universe itself cools down. The universe will keep cooling and make computers more efficient. Or so the reasoning here goes, and we discussed it in detail in our Civilizations at the End of Time series. But we might find some faster ways to move through time. We can never rule out time travel, and obviously a good way to escape entropy or running out of fuel or running into competition is to move back closer to the beginning of time. However, moving backward in time is a lot more problematic than moving forward in time, and we do not see any ancient universe-spanning civilization who moved back to the dawn times and began colonizing things when they were much closer together and just cool enough to survive in. That is not necessarily a deal breaker, but moving forward in time is not restricted at all. See our time travel episode for more discussion of the difficulties, but an object under known science can already move at tremendous speeds and experience slower time, or the same, exist in a place of tremendous gravity and move slower. They're not exactly jumping forward, they pass through time, and it is worth remembering that by default a backwards time traveler does too. You're just not popping out in some other universe and emerging there and then, so people could see you passing backwards and interrupt you, and you still interact with the universe around you, same as an ultra-relativistic spaceship can still slam into a piece of matter and explode. I sometimes think we get so hooked on discussing why backward time travel is impossible because it violates causality and energy conservation that we ignore that the actual process would almost certainly be lethal during the travel path itself simply from the ultra-high energy collisions. Since every particle is hitting you with either infinite travel energy or negative or imaginary energy, depending on your model, which would also be very bad. But we could imagine people figuring out a way to jump out of the universe for the trip, or are doing this forward journey in intergalactic space where they may never hit anything more energetic than a blue-shifted photon of cosmic microwave background radiation left over from the early universe. They are merely going very fast, not faster than light, so that is a survivable collision. It's just a very blue-shifted weak microwave photon. Just to make it into a mundane visible photon, which shouldn't hurt you, would require a shift of 1,000-fold in its energy. which also means time is passing 1,000 times slower for you when you hit it. Those leftover CMB particles are themselves redshifted ever weaker and cooler as the universe ages. They were emitted as visible and high-infrared photons when the last scattering happened about 300,000 years after the Big Bang. If you could jump forward in time to the end of the universe in one fashion or another, then taking your treasure trove with you to then is a good way to operate, and might be what happens to civilizations. They all pack up and leave till near the end of the universe. Moving to near the beginning of the universe would seem better, but does require backward time travel, and nobody seems to have done that. Of course, they might simply have achieved their goal of going to a younger and earlier universe without time travel by migrating to a new universe. We don't know if there are such universes or if it is possible to reach them, but it is reasonable to suggest that if a Big Bang could happen once, it could happen again, or had happened before. It also might be possible to create new universes underneath this one, what we call a subverse, and indeed this is what you're doing if you upload human minds into a virtual world running on ultra-core computing. Only here you're just making new matter and spacetime in whatever way it was done here in the first place again. A new Big Bang, not a computer simulation. A lot of hypothetical methods for doing this would require lots of mass and energy, so migrating to a galactic core to get the job done is one approach, and you might even have some massive gateway there that gets left in place for others to follow or reuse to make their own subverses or travel to other existing but younger universes. Now, speaking of different universes, we do have one other type of migration that, if possible, basically solves the Fermi paradox, and that is multiverse migration. If there really is a new universe for every possible timeline, or an array of universes for every possible state of matter and position for matter in the universe, then that's a lot of uninhabited copies of Earth. Just a very simple example, there may be 100 billion decently terraformable planets in this galaxy, and 10 billion galaxies we could potentially reach with highly relativistic spaceships. That is 10 to the 21 planets, a sextillion planets, a billion trillion planets we might claim in this universe. You could be a billion times better than that with Dyson swarms, and perhaps a billion times better than that with ultra-efficient computers running uploaded minds on virtual worlds, 10 to the 39 planets, or a duodecillion. There's almost a trillion times that many atoms on Earth, 10 to the 50, and we could imagine a timeline where Earth was identical to now, except for just one of those atoms being 1 centimeter over to the right, and so there's another identical timeline to ours for each atom in our planet's core that's just that centimeter over and no other difference. These 1 centimeter single atom shift copies of current Earth outnumber the total number of planets in the entire observable universe. There's a whole other set of copies of Earth where that same atom is just 1 centimeter to the left, up, down, diagonal, 21 centimeters over, or 42, or a whole kilometer, or just a nanometer. This isn't infinite, there is a minimum distance it can meaningfully move under quantum, but it is one of those numbers where just to write it down on paper would require so many sheets of paper that it would collapse into a black hole under the sheer mass. And this is not limited to copies of present Earth, which would be inhabited already, though I would note that invading a planet through a portal and claiming it for your own is still probably easier than sailing through the ocean of the night for centuries to forge a new one at the end of that journey on some godforsaken dead rock. That would be a difficult battle to win, but there's a timeline where things are the same for environment and geography, but science progressed a little slower, so you can go and invade the technological equivalent of the 19th century and roll through them easily. Or the 9th century. So too, there's a timeline where everything in history is basically identical but behind, so that you're effectively time traveling to a world identical to ours historically and politically at any given prior date. Indeed, there's one that's identical except it has a copy of you in it, and one for every other person, and one for every other person where just one atom in them was moved a bit over or missing too. Same planet, just a bit younger. You might do some astronomy and realize the CMB radiation or position of stars put it as here and now even though it seemed identical to Rome in the year 64 AD, and you can go put out that fire in the city and see what happens if Rome didn't burn down while Nero played his fiddle, or one where he played a drum instead, assuming that event is historically accurate, and historically inaccurate multiverses will exist too. Indeed, you should have multiple paths leading to the same present for the same reason you have multiple futures branching out from the present, as many roads can lead to the same place as out from it. But while a lone time traveler or multiverse traveler might revel in visiting other human civilizations on other copies of Earth, there are way more versions of reality where everything was identical until about 1 million years ago, and some humanish person was working with some sharp rock to cut things or strike a fire and accidentally cut themselves and died from an infection, or burnt their hand and didn't play with fire again, and that branch of humanity died off or got eaten by a tiger, or where that first proto-human or even first primate got eaten by a proto-tiger, and the world looks much like it did before humanity settled every corner of it, complete with dodos and maybe even mammoths, and just waiting for multiverse settlers to arrive. And there's a version of this for each atom moved 1 centimeter left, or 1 nanometer right, or 1 kilometer up, and indeed one for where just 2 of those atoms are differently arranged, or where Earth is missing just 1 or 2 atoms. 1 copy for each missing one, and each of those for where all the other atoms are rearranged a little too. Or an extra atom. Or Earth formed but 1 centimeter to the left itself, or formed 1 minute later, or our Sun did, or both did but 1 million years later, so we arrive on Earth 1 million years ago, and with a Sun that has an extra million years of life to go. Or 1 billion. Or one where it is just as old as now, but by insanely low, but non-zero odds, very little fusion had yet occurred, extending that sun's life. And critically, while there should be a vast number of planets where civilizations have arisen and developed the same technology and want to colonize worlds too, there should be vastly more where they did not arise, so you might bump into them but aren't likely to need to fight for space. See our Multiverse Warfare episode for more discussion of strange situations that can emerge from multiverse conflicts. This, if possible, becomes a vastly better option for settlement than other star systems do, and handles the Fermi paradox quite well, though with 2 caveats. First, this may be a one-way trip where you can go, but cannot really have open gates allowing constant easy movement back and forth, or even any after going, in which case space settlement may be harder, but some folks might prefer it anyway and thus still do it, so that they can stay in touch with their original civilization, even if it includes a lot of light lag. Second, if casual travel back and forth to copies of Earth are possible, then folks with access to such insane resources can afford a very robust space exploration department if they want to, including beacons that let other civilizations know they exist and what this cool multiverse tech is. One might rebut by saying they might not live in a universe with another civilization either, but then that's just the rare Earth solution of the Fermi paradox. Aliens are super rare, and with the icing on the cake being multiverse expansion is possible too. One last option for migration though is going to more fertile realities and dimensions than our own. We looked at this more in our episodes Aloof Aliens and Higher Dimensional Aliens, and we're already long on time today, so we'll summarize the key notion. As we discussed in our previous Fermi Paradox episode from last month on the fine-tuned universe hypothesis, there are a lot of reasons to think other universes exist that are different in their dimensions or values of their physical constants rather than just their timeline of events like classic mini-worlds multiverses. But there's also reason to think these would be barren of life and inhospitable to its formation. However, they might be very handy for power production or gaining mass from. Some civilization might stick to their homeworld or flee to the intergalactic depths because they can pull all the energy or matter they need from some barren universe and dump their waste matter or entropy back into it. And this is a pretty good option for the Fermi paradox too, along with being able to build Doctor Who TARDIS-like structures that are bigger on the inside than the outside, so pocket universes inside our own. But we don't know for sure that those universes are inhospitable to life forming, and more importantly, inhospitable to life forming is not the same as inhospitable to settlement by intelligent life. As an example, planetary orbits may be ultra unstable in 4-dimensional space, so they don't naturally occur much or last long, but you can create one that's very well aligned and exert station keeping to make it stay that way. Houses don't naturally form, you build them, and we may be able to make homes in other universes with different properties. And as a simple example of why you might migrate to one, if we found an otherwise identical universe where the speed of light was 100 times faster, ignoring the problems that cause with atomic scale interactions, you could settle that universe 100 times faster and keep your empire stable through communication and trade 100 times wider than here, and thus a volume 100 cubed or 1,000,000 times larger with 1,000,000 times as many planets and people. For analogy, you abandon your village-sized empire possible in this universe for a continent-sized one possible there. That's a pretty good reason to migrate, and we can come up with many others, but let's close on one key weakness to migration options that is not fatal but is a big one to keep in mind. We might find better places for us to expand to from Earth than the stars nearby us, but that doesn't mean we would ever abandon Earth itself. And as long as we hold this place and are gaining access to vast amounts of resources from other places we might migrate to, it only increases our ability to look out and see other civilizations that might exist, or be able to speak to them or be heard by them louder and farther away, or hear them if they speak to us from further away. And I don't think we would ever lose our curiosity about finding out if they existed, or that none of them would share that curiosity about us. So if they are out there, migrating or not, should we not be able to hear them? And if nothing else, should we not continue to look for them for now? We were talking about migration today, and for many of you, that migration will be happening soon for you or a loved one as the school year starts back up. If you're looking for a leg up on science, math, and computer science, whether it's the basics or advanced materials, then you should try out Brilliant.org. I doubt I need to tell anyone here how fun science can be, or how important it is in the modern world and workplace, but it can still be intimidating to learn, especially math, which is the backbone of almost all areas of science and technology, and even business and finance. But it doesn't need to be intimidating. Brilliant helps build real knowledge in minutes a day, with fun lessons you can do whenever you have the time, learn through problem solving and doing, with hands-on interactive content that's fun, immersive, effective, and intuitive. Plus, all the content on Brilliant is crafted by an award-winning team of teachers, researchers, and professionals from MIT, Caltech, Duke, Microsoft, Google, and more. You can trust Brilliant to help you on your journey for knowledge, but you don't have to take my word for it. You can try everything Brilliant has to offer for free for a full 30 days. Just visit brilliant.org/IsaacArthur or click on the link in the description. You'll also get 20% off an annual premium subscription. So that's it for today, but join us for Sci-Fi Sunday on August 11th as we examine the popular notion from sci-fi that humans might have been uplifted by distant visitors or some more ancient alien civilizations native to Earth. Then we'll be back to the here and now on August 15th to look at what the next technological revolution will be. After that, we'll be looking at the topic of space warfare to explore the role and makeup of battle fleets on August 22nd. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like Jupiter Brains and Megaminds at go.nebula.tv/IsaacArthur. As always, thanks for watching, and have a great week.